Okay, in this video we'll be looking at complex numbers as 2D vectors. Okay, so back in chapter 6 when we started talking about complex numbers, we saw that complex numbers can be written in this form. Okay, this is probably the form that you've seen the most when we talk about quadratics and imaginary roots. That's when we first started talking about complex numbers. Basically, we have two parts on a complex number. The A is the real part and B is the imaginary part. Okay, it's always attached to the I, the imaginary number, and we represent A as the real part of Z, like this, and B as the imaginary part of Z, like this. Okay, and we can represent complex numbers not only in this form, but we can also represent them on a complex plane as vectors. Okay, so basically, if we have a complex number, we can write those two numbers as a point on the Argand plane. We talked about this before, but the Argand plane is the plane where the x-axis, the horizontal axis, is the real axis, and the vertical axis is the imaginary axis. So you can think of this axis here as having all the real numbers. Okay, all real numbers go on this line. But every number could also potentially have an imaginary part to it, and so that part goes on the in the vertical direction. And so we can represent a complex number with those two components, the real component and the imaginary component. And when we represent that point on the Argand plane, that point can also be represented as a position vector starting from O. Okay, and so this vector here would represent the vector AB, or the complex number A plus BI. All right, so here are some examples. If I have Z1 is 2 plus 3i, and I want to plot that as a vector on the Argand plane, okay, what I can do is I can look at this becomes my x component, this becomes my y component, so it would be 2 and 3. So that would be my point, and that would be Z1. Okay, Z2 would be 4 down 1. Okay, so that would be Z2 minus 3i. Since there's no real part, I don't move on the horizontal axis, and I just write down the vertical component. And so that would be 1, 2, 3 down here. That would be Z3. Okay, Z4 would be minus 3, minus 1. Okay, so it's pretty simple. It's just plotting points, and it's really the position vector of the point. Okay, this is Z5 here because that's 3, and there's no real imaginary part. Okay, so operations with complex numbers can be done using vector operations. So it's pretty much the same. Since we can represent complex numbers as vectors, we can apply the same operations on these complex numbers. The same operations that we would if they were just regular vectors. Okay, so let's look at this example here. If Z1 is 3 plus I and Z2 is 1 minus 4i, okay, let's use both algebra and vector methods to find out what Z1 minus Z2 is. Okay, so algebraically, what would this look like? This would be Z1 minus Z2, right? So Z1 would be 3 plus I, and if I were to subtract Z2, that would be 1 minus 4i. Okay, now remember here that I don't know if we talked about this, but basically when we're doing operations on complex numbers, we add real parts together and imaginary parts together. We can combine those, right? So we would do 3 minus 1, since that would be we'd have to distribute this minus sign here. So it would be 3 minus 1, and the imaginary parts would be added together, so we'd have plus I plus 4, so that would be, I guess, let's just write it like this, plus 1 plus 4i. Okay, and I would factor the i's out here. Okay, so this would become 2 plus 5i. Okay, and if I were to use vector methods to do this, z1 would be 3 plus I, so it would be 1, 2, 3 plus 1. Okay, so that would be z1. Z2 would be 1 minus 4I, so it would be 1, 1, 2, 3, 4. Okay, that would be z2. Alright, so that's z2, and there's z1. Now what is z1 minus z2? Okay, so I have to take z2, flip it, right, and then add it to z1. Okay, so it would be z1 minus z2, that would be minus z2. I flipped it, and then I moved it. Okay, so it would be 1, 2, 3, I guess it would be up here 4. If I were to move this up, and go up 4, there you can see it would be, that should be 2. Okay, so that point right there would be 2 and 5 up. So you can see that that also works. This vector right here, let me change that to a different color. That vector right there would be the vector z1 minus z2. Okay. One more example here. If I were to do z minus 2w, where z was 1 plus 2i and w was 3 minus i, okay, we would do the same thing. We would just write z minus 2w, z becomes 1 plus 2i, minus 2 times, and I just substitute 3 minus i, so algebraically that would be 1 plus 2i minus 6 plus 2i, and so this would become minus 5 plus 4i. And if I were to do it with vectors, you would see that that would also be the case here. Okay, so let me just show that to you here. If I were to do 1 plus 2, that would be 1 plus 2i, that would be this vector here. Okay, 3 minus I, so I would go 1, 2, 3, down 1. There's my, this would be my z vector. Okay, this is z and this is w. And if I do z minus 2w, so let's see, what would w look like? It would be pointing in the opposite direction. So this would be w, this would be minus w. Okay, if I had 2 of those, that would be 1, 2, 3, and up again, so it would be probably right here. Okay, now that would be minus 2w, so if I add that to z, okay, that would be up here somewhere. Okay, so if I were to count the squares appropriately, I would get minus 5 and up 4. Okay, so that should be the vector minus 5